we are going to try out this TJC paper. Okay, I find this TJC paper 2 section A a very interesting section, because the questions aren't easy, and yet they are the very I mean, I find the way the questions that are set in this TJC 2020 section A of their paper 2, like really very witty. I think the teachers really spend some time to think through the question and then trying to make it a little bit tricky, but yet if I were to be not doing this as an exam paper, it is actually quite enjoyable. Looking at how certain hints are given throughout the questions, and then how we can probably not as directly, but probably pick up those hints and then try to solve for whatever that the question is requiring us to solve. Yes, hello. I'm also hoping that okay, in a way, I do hope that the A level this year can be easier. But at the same time, right, I don't actually wish that it is that easy, because if the A level paper is that easy, then the playing field is going to be very flat. And when the playing field is very flat, when the playing field is very flat, right, then it just makes it less easy for those students who are more prepared and hardworking to do well for the paper. So I'm hoping that it will be like the last few years, where the first few questions are, yes, they are a little bit easier, and hopefully they can be easier than even the last few years, but there should be some questions that are a little bit more tricky, and if our concepts and basics are well grounded, then we should be able to do pretty well for our A levels this year. Oh, Claire, you are asking me whether I do O level math, as in like we did it last time at Achevas, but we have stopped for about 4 years, I think 4 to 5 years. So currently we are focusing only on H2 math, but I'm still doing the O level TYS. Partly is to share the solution. Another reason is also so that I can still be in touch with the O level, because J1 students are ex O level students. Then at least I know what is their background. At least I can roughly tell what kind of O level A math paper that they have gone through. Okay, anyway, let's take a look at this TJC 2020 paper. I think question number 1 is already a pretty interesting question. I don't think it is difficult, but it's just interesting. The way that the information is passed on to us is that little bit different. It is given to us in this question number 1. Hang on. Okay, it is given to us in this question number 1 that we have a sequence, and let's be clear that a sequence is literally a sequence. The question didn't tell us whether this sequence is AP or GP. It may be an AP, or it may be a GP, or it may even be some other sequence. We are not sure, so let's not assume anything extra. Assume beyond what the question is trying to tell us. So we have U1, U2, U3 as a sequence. The sum is Sn, which means that Sn, which is in the summation notation here, represents U1 plus U2 plus U3 all the way until Un. And in part 1 here, it is known that the first 3 terms of the sequence is 17. The first 3 terms of the sequence, we are talking about U1 plus U2 plus U3. This is equal to 17. And if I were to make use of the notation Sn, this is S3. So this is the first piece of information that is given to me. I am going to be expecting more information to be given so that I can find the first 3 terms of the sequence. The question also tells me this. The question tells me that the summation from n is equal to 1 all the way until 3 of Sn. This is equal to 30. I do find this sort of tricky, because if we get too hasty in in writing down this based on Sn, we may very carelessly see this as another U1, U2, U3, which is very weird. So this is sort of like a sum of the sum, which means that we are talking about S1 when n is equal to 1, then plus S2, then plus S3. This is equal to 30. And what is S1? S1 is U1. And as for S2, S2 is U1 plus U2. And S3 is U1 plus U2 plus U3. We can definitely write that, or to keep it simple, let's just go for 17, since we know that S3 is equal to 17 from the first piece of information that was given. So this is equal to 70, which means that 2U1 plus U2, this is equal to 13. And now we have one equation number 1. We have our second equation number 2, and the third equation is going to be from this sentence here. It says that the third term of the sequence is twice of the first term. So let me keep a spacing. U3 is going to be equal to 2 times of U1. So my third equation will be 2U1 minus U3. This is equal to 0. This will be my third equation, and we just need to press this into our graphing calculator, and we will be able to get U1, U2, and U3. From the calculator, U1 is 4, and U2 from the calculator, this is 5, and U3, this is equal to 8. Oh, it is okay, Alvin, you don't have to send me anything. I'm not going to be looking at the O-level paper now. I will be concentrating only on H2 math at the moment, and we are preparing, we are really gearing up to prepare ourselves for one more week before H2 math paper. So, and then I'm also going to be preparing for the 5th of November workshop that probably most of you are attending. Okay, anyway, I will press it into the calculator, and this is what we are getting: U1, U2, U3. It is a system of linear equation question. Next, okay, we have already done the first part. Next, part 2. A constant k is subtracted from each term of the sequence, so that the first 3 terms, we are still working on U1, U2, U3. So that for the first 3 terms, let me just keep them here first. For the first 3 terms, each of the term is going to be subtracted by k, and now these first 3 terms form 3 consecutive terms of a GP, which means that for this new sequence, we are looking at the first 3 terms. So U1, which is 4 minus k, and then we have a 5 minus k, and then 8 minus k. Okay, these 3 terms, U1, U2, U3, from the first sequence, these 3 terms are going to form 3 consecutive terms of a GP. If this were to be forming 3 consecutive terms of the GP, that means the common ratio of the GP can be found by taking the term 5 minus k, this divided by 4 minus k. It can also be 8 minus k divided by 5 minus k. So we have an equation here in terms of k, and I believe we can make use of this equation to try to solve for k, which is what the question is asking for. And then subsequently, with the value of k, I can probably sub it back into either this expression or this expression to find r. So let's focus on this first. And if I were to cross multiply, we will have a 5 minus k square. This is going to be equal to 4 minus k multiplied by 8 minus k. So expanding this, 25 minus away 10k plus k square is equal to this. Expanding it, this times this is 32. Then we have a minus 4k minus 8k. This is minus 12k plus k square. So I guess k square and k square will disappear. If I were to bring the 12 over to the left hand side, we will have a 2k. And this, if I were to bring 25 over to the right hand side, this is 7. This tells me that k is equal to 7 over 2, which means that the common ratio, we have already found k, and the common ratio is going to be either this or this. Let's just make use of the first expression. So 5 minus away 7 over 2 divided by 4 minus away 7 over 2. So the common ratio in this case is R. An interesting question. Not that difficult, but interesting. And I do hope that this kind of question can appear in the A-level this year. Because this is the kind that I will consider it as easy. But if your foundation is strong, then you will actually see this as, okay, I won't say this question is easy, okay, but if your foundation is strong, then you will find this question very manageable and maybe even easy. So, I do favor this kind of question. Next, question number 2. Question number 2, we have a functions question. We have fx that is given to us as this, gx is given to us as this. First, we are supposed to sketch fx. And to sketch fx, what I've been talking about during my tuition classes was that if it were to be a standard graph, it is good that we try to train ourselves to sketch these standard graphs without using our GC at all. So maybe we can practice it here on our live stream also. Let's do a quick sketch of just this. We're not with the domain, but just this. So this is a quadratic equation. A quadratic equation with the coefficient of x squared as -1. So we will be expecting a set face parabola. A set face parabola with the maximum possible point here as 2 and 5, right? 2, 5. And if we were to be drawing the parabola here, this is when x is equal to 0. When x is equal to 0, we have 5 minus 2 squared, so it is going to be 0, 1 for the y-intercept. And as for these 2 points, we can definitely press into our calculator, or if I were to let y to be equal to 0, so I will have this square. If I were to let this be equal to 0, x is going to be equal to 2 plus or minus square root of 5. So this point here will be 2 minus square root of 5, 0. And this point here will be 2 plus square root of 5, 0. It's just a practice to sketch standard graphs. So, okay, anyway, we have already sketched this, but of course in the exam, I will definitely want to sketch this into my GC to just make sure that I'm totally correct. We are working on fx, which takes up the expression of this, and the domain is such that x is supposed to be less than or equal to 3. So less than or equal to 3 should be here, right? 2 and then 3. So let me sketch this graph. Okay, part 1. Yeah, please, you should use your GC. Oh, as in like, why do I suggest that why do I suggest that we learn how to draw our standard graphs, right? Because we want to recognize that if I were to depend on my GC to draw standard graphs, that means I will have one less thing that I'm prepared for the A-levels. Because standard graphs are graphs that are part of our preparation, and like what I was telling my tuition classes, right? It is actually not very strategic to try to plan to get A for A-levels. If you plan to get those A during the A-level itself, you should try to plan so that you get as much of the A's that you plan to get before the A-levels. That is about preparation. And for certain things that we are expecting to appear in the A-levels, we can actually prepare for them first. For example, one very simple thing that we can prepare for are standard graphs. And if you were to be reading enough scripts, you'll be surprised how often standard graphs are actually drawn wrongly in prelims. And the reason is because students depend too much on their calculator, and the calculator is leading them to get an A, but that A, we can actually get it before I even see that standard graph appearing. So one thing that I know is, before I even press the calculator, I'm already expecting all the key features of my standard graph. So if it is going to be a function question where I need to draw the graph, I'm already expecting, like how the shape is going to be like before I press on the calculator. I know where I'm supposed to find all the asymptotes and where I'm supposed to find all the key features. So I don't have to react, wasting that few seconds during the exam to work on graph as if I've never seen those graphs before. So, I mean, it is just being over-prepared, but definitely in the exam, we will still press this into our calculator just to verify, especially when it is an A-level. I will definitely press in the calculator. Sometimes I want to laugh at myself during major exams. Even things that is like 3 plus 9, I will still press into the calculator. But anyway, let's just sketch this. My y-axis and x-axis. And I know that my graph is going to be something that is like this. So I'm going to make sure that I sketch my standard graph with the help of my calculator, where here is 3 and the corresponding y coordinate is 4. 4 is higher than this 0, 1. So I'll make sure that this is higher, or else I will see some students in the A levels, they will draw this, and then what if this point accidentally falls below 0, 1 or at the same level as 0, 1? I've seen marks being minus off in prelim script, where this point falls below. I mean, for instances that are like this, where the reference positions of the points are incorrectly written in their scripts. So anyway, I have this, and then this point here is 2 minus square root of 5 and 0. So this is my graph. Y is equal to fx. The origin is here, the x coordinate is here. And okay, I've indicated everything and explained why f inverse does not exist. We're going to pick a line that's going to cut the graph at more than 1 point. I think I can pick the line y is equal to 4. So since the line y is equal to 4 cuts the graph of y is equal to fx at more than 1 point. Therefore, f is not a one-to-one function, and this implies that f inverse does not exist. Okay, I guess this is pretty simple, so 3 marks. Next, part 2, explain why the composite function fg exists for all real values of x. Why the composite function fg exists for all real values of x. We have a schematic for our analysis of composite function. I've used that on the Achevas TV theory outline, and I'm going to continue to use it here to process this composite function. So one function is going to be connected to another function. We are talking about the function fg, and x is going to go in this direction. That means x is first going to go into g, then after that f, which means that for this connection to work, I want to make sure that everything that comes out from g will be able to go entirely into f. So the range of g, I want to make sure that it is going to be a subset of the domain of f. The domain of f we have, it is x is supposed to be less than or equal to 3. What we are not sure about currently is the range of g. So to find the range of g, let's sketch this graph. In fact, this is also a standard graph with a bit of transformation from the basic graph e to the power of x, but we can definitely try to sketch this into our calculator, and we will be expecting asymptotes. In fact, a horizontal asymptote, if you are familiar enough with this standard graph, and the horizontal asymptote is when x tends to positive infinity, and I'm going to be getting this to be equal to 0, and gx is going to tend to 3. So I'm not able to draw gx because I don't really know what is the domain. So what I'm thinking of is we should probably still do a sketch, but let's do a sketch of the graph of y is equal to 3 minus e to the power of minus 2x. Good. Again, I want to stress that I'm sketching this where x will take up all real numbers, because I'm not able to sketch g due to the fact that I do not know what is k yet. So sketching this, we have a horizontal asymptote like what I've discussed, and we will try to sketch asymptotes first. From my calculator, I can see that the graph tends towards the horizontal asymptote. That is when x goes to positive infinity. When x goes to positive infinity, this becomes 0. So y is equal to 3 is going to be the horizontal asymptote. I can see from my calculator, or if you are doing a bit of transformation with from the standard graph, y is equal to e to the power of x. The graph is going to be like this, with the x-axis as somewhere here. And if x is supposed to be less than or equal to k, we can see from this graph, the graph of y is equal to 3 minus e to the power of minus 2x, that regardless of the place that I position k, for example, I position k here, if I were to position k here, then the y coordinate is going to be gk, correct? The y coordinate is going to be gk. So from our graph, we can see that the range of g is going to be from minus infinity. The y coordinate will go from minus infinity all the way until the y coordinate gk, because x is supposed to be less than or equal to k. So the range of g is going to be from minus infinity all the way until gk inclusive of k. And from our analysis, we can see that this gk, the value of gk, whatever value it takes up, it has to be a value that is less than the horizontal asymptote's value 3. So gk will definitely be less than 3, which means that if I were to quote the range of g again here in one single statement, comparing it to the domain of f, the range of g is this, and it will be a subset to the domain of f, because the domain of f is going to consist of everything that is from minus infinity all the way until 3 inclusive, and this gk is strictly less than 3, so it is definitely a subset. Therefore, we can say that a composite function fg exists. And part 3, we want to find the maximum possible value of k such that fg is a one-to-one function. I think there is no choice. We have to find the expression for fg in order for us to gauge. We have to find the expression for fg, and then we should try to sketch the graph of fg in order for us to analyze when fg will be or will not be a one-to-one function, depending on the domain that we are going to be giving. And because we are analyzing fg, so like what we were saying, let's try to find the expression for fg first. And fg is going to be putting g into f, so we have a 5 minus away x, which is going to be replaced by 3 minus e to the power of minus 2x. Then this minus 2 square. This is the expression of fg, which is 5 minus e to the power of this is going to be 0, so e to the power of this, hang on, oh sorry, I'm going to let it be this. So 3 minus 2, this is going to be 1 minus e to the power of minus 2x squared. This is the expression of fg, and we should also try to quote the domain of fg, which is the same as the domain of the first function, domain of g. And domain of g is going to be from minus infinity all the way until k inclusive. So now we can sketch fg, but now we still cannot sketch fg because we don't know what is the domain of g. So we are going to sketch the graph of y is equal to 5 minus 1 minus e to the power of minus 2x. And if you were to sketch this graph, from the GC, we can also see that this graph has a horizontal asymptote. And the horizontal asymptote is when x tends to positive infinity. When x tends to positive infinity, this will become 0. So it will be 1 minus 0, and it will be 5 minus 1 square. So the horizontal asymptote is going to be y is equal to 5 minus 1, 4. So we have this, y is equal to 4. From my GC, I can see a maximum possible point here. Then you will be going back down and then tending towards the asymptote. And from my GC also, this point is 0, 5. Or you can definitely let x be equal to 0. So it will be 1 minus 1. That means the y coordinate is going to be 5. And this is the graph of not yet fg. This is the graph of 5 minus 1 minus e to the power of minus 2x squared. And from this graph, in order for me to make sure that fg is a one-to-one function such that the domain is when x is less than or equal to k, the maximum possible k can go should be here, right? It should take up the x coordinate of this point so that anything towards the left is still going to be a one-to-one function. So for part 3, the maximum possible value for k is going to be equal to 0. Here, 0. And part 4, sorry. E to the power of 2x. E to the power of x is this. This is the graph of y is equal to e to the power of x. So if it is e to the power of 2x, it's going to be a scaling by a factor of half parallel to the x-axis. So let's say this graph is being squashed, half. The shape is still going to be the same, so I'm going to just conveniently use the same thing. And then if we were to replace x by minus x, that means this graph is going to be reflected about the y-axis. So we will have this. So it is going to be this, and then with a negative, the graph is going to be reflected about the y-axis. Then with a 3, the graph is going to be translated by 3 units in the positive y direction. And so I think the smiley face that you are saying, right, is you are looking at it as if it is e to the power of 2 mod x, maybe. So if you are looking at it from this perspective, then maybe it is going to form some kind of smiley face. I'm not sure, but yeah, my reply is no. It is not going to become a smiley face. Okay, so now maximum possible k is equal to 0. Let's continue. For the value of k found in part 3, find the value of x for which fgx is equal to fg inverse x. So for the value of k that is found in part 3, which is 0, that means we are going to be working on, let me just write it here. So we are going to be working on okay, let me be a little bit lazy. So I'm going to remove this. So we are going to be working on fg with this expression. And the domain of fg is going to be this. So we are going to be working on x to be less than or equal to k. And k is going to adopt the value from part 3. So x is supposed to be less than or equal to 0. Which means that the graph that we are going to be working on is going to be this red colored portion. Let me redraw this. Okay, I think this is a important graph for us to do our next analysis. So we are going to be looking at from here, then coming down this way. So we have a 0, 5 here. This is the graph of y is equal to fgx. And we are supposed to be solving for, let me erase this. We are supposed to be solving for fgx is equal to fg inverse x. So let's draw the inverse graph of this. If it is the inverse graph of this, it is going to be a reflection about the line y is equal to x. So the line y is equal to x is here. This point is going to be reflected to here, which is 5, 0. and my graph will look something that is like this. Okay, this is my graph of y is equal to f g inverse x. So now based on the graph, we can see that the place where fgx is equal to fg inverse x is this point that is here. So knowing that it is here, now solving for fgx is equal to fg inverse x. I can do an improvisation. Instead of solving for this to be equal to this, I'm going to be solving for the x coordinate of this point by letting fgx be equal to x, which is the intersection between this curve and this line. So most likely in my calculator, I already have this in my y1, and I'm going to press this into my y2. So from my GC, I can solve for x, and the value of x here is equal to, let me see, is equal to negative 0.607, and that is for part 2. Okay, so question number 2. Next, let's move on to question number 3. Question number 3, we have this is a Maclaurin's question where instead of giving us as y, this question gave us fx and then f prime x, then f prime prime x. This is a simulation of that question that came out in the A levels. Goodness, which year is it? Is it the year 2016 or 2017? Right, there was a Maclaurin's question that came out which has this. They use notation fx f prime x instead. So we can, to make it a little bit more familiar, we can definitely let y be equal to this. So we will be proving this, then d square y dx square, then dy dx, then y. Okay, we can definitely do that. But let's do a simple practice together about to see whether we are able to adjust to different notation that maybe A level will give us this year, something that we have never seen before, and we just got to adapt to just try to manipulate those notations instead. What I mean is I'm going to try to continue with this entire question. Instead of replacing fx by y, I'm going to just continue to make use of fx. So we have this ln 1 plus x. And in order for me to get this, I'm going to be differentiating this twice. But before that, I think I will want to do an improvisation to this equation. I'm going to do a sine inverse on both sides. So it will be sine inverse fx. This is equal to ln of 1 plus x. Okay, and I think this is going to make it easier for us to get this. So by doing this, let's try to do a differentiation with respect to x. So on the left hand side, when I differentiate this with respect to x, it is going to be 1 over square root of this square, 1 minus this square, so 1 minus this square. Then by chain rule, I'm going to differentiate this. So f prime x is equal to 1 over 1 plus x. We can definitely continue to differentiate this, but if you were to look at what you are supposed to show, we don't really have like fractions. So why not let's remove the fraction by cross multiplying this. I'm going to multiply this across, so I have a 1 plus x, then f prime x. This is going to be equal to square root of 1 minus then fx square. I can already continue with my differentiation, but I do see a 1 plus x square here, and this square root just makes the differentiation sort of a little bit more tedious. So I'm going to make another manipulation before I differentiate. I'm going to square the entire equation. So squaring this, I have a 1 plus x square. Then we have a f prime x square. And now I don't have this square root to manage anymore. And I'm ready to differentiate. Differentiating once again with respect to x on the left hand side, product rule. Let me start here. Product rule, I will have a 1 plus x square. Differentiating this will be 2. Then f prime x to the power of 1. Differentiating this again via chain rule, f prime prime x. Then continue with my product rule. I'm now going to differentiate this, which is going to be 2, 1 plus x to the power of 1. Then this remain constant, f prime x square. This is going to be equal to minus 2 fx to the power of 1. Differentiating this, f prime x. And if you were to look at this entire equation, we can actually divide throughout by 2, and we can divide throughout by f prime x. This one is very misleading. So f prime, for a moment I thought this was a prime, but this is 1. Let me erase this 1. Okay, so I mean, since it's to the power of 1, so it doesn't really make a difference. So I'm going to divide throughout by f prime x also, f prime x, dividing by f prime x, dividing by f prime x. So now we have a 1 plus x square f prime prime x plus, this is a 1 plus x, then f prime x, and this is equal to minus f prime x. Yep, we have shown by moving this over to the left hand side, it will be what the question wants us to show. So this f prime prime x plus 1 plus x, f prime x plus f prime x. This is equal to 0. And we need to understand that for us to be doing something that is like this, and all these few steps here are executed at a pretty high level, it is something that, I mean, since today is the A level, it is something that you don't do in, not A level, since today is the O level A math paper, this is something that you don't often do in a A math differentiation. That is why in tuition, you know, I always like to make sure that the students know that at H2 math level, when we are trying to learn differentiation technique, let's not be sucked into learning differentiation technique as if we are really trying to relearn product rule, quotient rule, chain rule, or even making use of new standard results to do differentiation, because the process, although the standard results are new, but the process of differentiation is still going to be exactly the same as your secondary school. That is why the essence of differentiation technique at H2 math level is not going to be just or the technique itself. The essence of differentiation technique is banking on the fact that we are supposed to have enough experience, and then looking at a question that is like this, we make decisions. We make decisions based on foresight that we have acquired through our experiences since our secondary school. And you know why we need a foresight to do a question that is like this? You know, wait, did I do something wrongly? Prime fx. Oh, okay, this was a mistake. So this is fx. Then so no more prime here. Okay, so this is my fault, fx. So oops. So this fx. Okay, so fx, shift it over to the left hand side is fx. So for example, right, like hello, you find this difficult, and I don't think it is the differentiation that makes it difficult. What that is difficult is probably those steps that I try to draw in green color. And what is so special about these few green colored steps? These few green colored steps is executed because we are supposed to be getting a f prime prime x. That's the reason why we need a foresight. It is not because we want f prime x. In secondary school, they focus a lot on f prime x, which means that the moment when you are given an fx, basically you just need to do differentiation blindly, you will be able to get the marks. But in order for you to get an f prime prime x and then getting it in the form of an equation that is as complicated as this, you need to plan your steps. You need to come up with a rough strategy so that your entire process is efficient. This is H2 math differentiation. And how do I plan my strategy? I know I'm going to be differentiating this equation twice. And I know that when I differentiate this twice, what that will make this more complicated is product rule, quotient rule. Chain rule is actually pretty okay. It is usually product rule and quotient rule. So if I were to differentiate it from here, as if I don't plan, I will do it exactly like my secondary school. That means my focus is only going to be on f prime x. And when I differentiate it this way, I will have one function put in another function and place in another function, which means that I will be expecting, although it is not going to happen for this case, but I will be expecting 3 terms being multiplied together due to chain rule. Is f prime x problematic? No, it is not. What that is problematic is because this question asks us to go for f prime prime, which means that if you don't plan with 3 terms being multiplied together, f prime prime x is going to be a problem. It is going to be very tedious because you're going to be doing a product rule to 3 terms being multiplied together. That is why I went from here to here. Because of implicit differentiation, and because in this case, because of sine inverse that we have learned, I distribute the burden of composite function to both sides as much as possible. Instead of cramping everything on one side such that I'm going to have a lot of chain rule, I brought this sine over to the other side so that I can have one less chain rule to do, so that I will have one less product to multiply, so that I have less to do when I execute product rule. So for those of you who are looking at this and you find this tedious, I would suggest that for the next 1 week, do spend some time to take a look at your Maclaurins again and then see whether you can make some adjustment to, because there's no rules, no strict rules to follow. It is more of like that gut feeling of how you want to manipulate and strategize your differentiation. So do give it a try, because I do think that as long as you try it once or twice, you can follow an example that is like this, then it is actually going to be pretty easy for you to continue to find a way to do whatever manipulation and decision making that you need. Find direct. Okay, I'm not very sure what you mean by finding direct f prime x and f prime prime x. I think I will not go for finding direct. That means I'm assuming that find direct means you will find this first. Then for whatever expression that you have, right, then you find f prime prime x. This is, I mean, you may get the answer. I'm not sure because I didn't try. But I believe that your answer is going to be sort of like tedious, because ultimately after you have found this and found this, you are prepared to sub it into the left hand side and show that it is equal to 0. And this is just going to be a 3 marks question. That is not usually how we want to try to manage our time, because our time is managed by making sure that we train to get a lean solution. We don't train to just get an answer, because if you train to just get an answer, I may run out of time to check during my A-levels. And I know that if I can plan so that I can have 30 to 45 minutes left to check my paper 1 or paper 2, it will immediately increase my chances of getting A by quite a fair bit. Many mistakes and carelessness can be found if I were to be given just that 30 to 40 more minutes to check. Okay, so my suggestion is don't just depend on this particular question. Go and look up all the Maclaurins that you have done before. Look at the implicit differentiation that was done in the first part. Try to plan. Try to plan and ask yourself, what can I do to the equation such that I can get d square y dx square faster and easier. And you will realize usually it is when they ask you to show d square y dx square that is going to make that question more tedious for those of you who don't plan. If they were to ask you to show dy dx, most likely you're going to get it correct, because it's just one step and there's no planning necessary. You can manipulate, or you can just differentiate directly, you're still going to be getting the answer. Okay, goodness, I don't even know why I have talked so much about just this part 1. Let me quickly continue for the next few parts. So we have gotten this. I better write down some of the terms because I think we do need some of the terms. We want to find the first three non-zero terms. The question did hint to us that we need to do a few more steps of differentiation, but I don't think I'm going to just immediately differentiate it first. I'm going to see where are the non-zero terms first. So before I continue, let me look at f0. And f0 is letting this be equal to 0, so it will be sine of ln of 1 plus 0. So ln 1 is 0, sine 0 is going to be equal to 0. And I'm going to find out what is f prime 0. So this is already a 0 term. So we need first three non-zero term. Hopefully f prime 0 is not going to be 0. F prime 0, I think I'm going to just make use of this. So f prime 0 is going to, let me just make use of this. So it is going to be equal to square root of 1 minus 0 square divided by 1 plus 0. So f prime 0, this is equal to 1. And let's look at what is f prime prime 0. F prime prime 0, shifting this over to the right hand side, we have a minus 1 plus 0 of f prime 0, which is 1, minus away f0, which is 0, this divided by 1 plus 0 square. And f prime prime 0, this is going to be equal to minus 1. Okay, let me keep this. These are the values that I've gotten. So with these values, I know I have only gotten the first two non-zero terms. We need one more. That justify why we should differentiate this again. Differentiating this one more time. So keeping this constant, I have a 1 plus x square. Then differentiating this gives us f prime 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 x. Then plus 2 times of 1 plus x to the power of 1. Then f prime prime x plus 1 plus x. Then differentiating this, f prime prime x plus differentiating this, it is 1. So f prime x, then plus differentiating this is f prime x. This is equal to 0. So this is going to be this square f prime 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 x plus this is 3 times of 1 plus x, f prime prime x plus 2 times of f prime x. This is equal to 0. By the way, if what I did just now using all the f prime like now, or at least for part 1, if sticking to fx, f prime x is confusing or unfamiliar, if something that is like this were to appear again in the A level, I would suggest to you guys to go for y is equal to sine of ln 1 plus x. I will suggest this, then prove everything in terms of y. Then after that, replace all the d square y dx square by f prime prime f prime. Okay, at least try something that is a bit more familiar. I think that is going to be better and more accurate for the A levels. But still plan, okay, the improvisation, the manipulation that I was talking about is not going to replace, even though we re-express this fx as y. So anyway, now I've gotten another expression, and from this expression, let me see whether we will get our next non-zero term. So this is going to be minus 3, 1 plus 0. F prime prime is minus 1. So minus 1 plus 2 times of 1, this divided by 1 plus 0 square. F prime 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 0 is equal to 1. So we have 1, 2, 3, 3 non-zero terms. And this will give us the first 3 non-zero terms of fx. f0 plus f prime 0 x plus f prime prime 0 divided by 2 factorial x square plus f prime 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 0 divided by 3 factorial x to the power of 3, and so on. So fx is going to be this minus 1 over 2x squared plus 1 over 6x to the power of 3. This is fx in the Maclaurin's expanded form, and we are supposed to verify this. We are supposed to verify this using the formulas from our MF26. And okay, I don't think that is very difficult also. Part 3. We are supposed to verify the fx using the formula from the MF26 is this. So this is going to be sine of ln 1 plus x. And in our MF26, we can find ln 1 plus x. So I'm going to replace ln 1 plus x by what we have in our MF26, that is x minus x squared over 2 plus x to the power of 3 over 3. And in our MF26, we have sine x. So I'm going to replace that sine x, the x in the sine, by this. And expanding it using the MF26 formula, this is going to be x, which is going to be replaced by this. Over 3 plus dot dot dot. Then minus, this will be x divided by 3 factorial cube. So it will be x minus x squared over 2 plus x cubed over 3 divided by 3 factorial, and so on. We are going to expand until the x to the power of 3 terms. So this will be this minus x squared over 2 plus x to the power of 3 over 3. The rest of the terms I'm going to ignore. Minus away this to the power of 3. The first term is already going to be x to the power of 3, and the rest of the expanded term from here will be more than x to the power of 3. I'm going to ignore all those. So I have this divided by 3 factorial, which is 6. So this is going to be x minus half x squared. This is going to be plus 1 over 6x to the power of 3. So I've shown that using MF26 formula, I'm going to be getting the same thing as this. Not necessary, because according to what the question says, right? According to what the question says, we want the first 3 non-zero terms. And if we were to be looking at the Maclaurin's formula, we know that for the first 3 non-zero terms, we know that from what we have derived so far, we already have f0. f0 is a 0 term, f prime 0 is a non-zero term, f prime prime is non-zero, and then f prime 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 is also non-zero. So we already have gotten our first 3 non-zero terms. So I don't think it is necessary for you to go on to differentiating it 4 times or differentiating it 5 times. Yes, that is actually what I did. Because I have let okay, so so yes, it is definitely possible. That means going for this to be the x term first, right? You're going to get the same thing. So it will be like ln minus ln cube divided by 3 factorial, and then ln will be replaced by this. I don't think so. You know why, Claire? Because, right, there's for writing purpose, you can do it for practice purpose. But what I do realize, right, since Claire, you are talking about this, what I do realize is according to what we did here, before I differentiate, I let x be equal to 0 first to check whether I have gotten a non-zero coefficient, which was what we did here, then here, then here, then here. So we did a check before we continue to do differentiation, and I think this is more efficient instead of what I see some students do, right? Which is okay, to get the first 3 non-zero terms, right, I'm going to differentiate it a few times, then let x be equal to 0, and then then we will see ultimately which are the terms that is going to, which are the differentials that are going to be equal to 0, which means that you may over differentiate unnecessarily. And that is why my suggestion is, if they were to ask you for the first 3 non-zero terms, like for example this case, differentiate, let x be equal to 0, then differentiate again, let x be equal to 0, so you know exactly when you need to differentiate again. It is different from those kind of Maclaurin's question where they ask you to expand all the way up to the x cubed term, so you know that you're going to be differentiating it 3 times. So a slight change in strategy, when they ask you to find the first 3 non-zero terms. Yeah, if it is not for this question, go ahead, and try to do practice all the way until d4y dx4 d5y dx5. But I think it's going to be very tedious, Claire. I'm not sure. Let's see. I think, yeah, it's going to be very long. Okay, I'm going to leave it to you to do it as a homework. Part 4. So for part 4, we are going to be making use of the previous answers, from the answers from part 2. So integrating from 0 to 2 of fx. If I were to go for part 2, this will be approximated as integration from 0 to 2. From part 2, we have gotten fx to be approximated to an expression that is this minus this, then plus 1 over 6x to the power of 3. And if I were to press this into the calculator, I'm going to get a 1.33. And if I were to use the more accurate version, it will be integrating directly sine of ln 1 plus x. And if I were to press this into the calculator, I'm going to get a 1.15. I don't think this is a very close approximation. Furthermore, we are doing 3 SF and they are not even similar. So why is it not a good approximation? Let me just show you what I've copied down from TJC, okay? Because we are working on larger values, that is why. Okay, because we are working on larger values of x. For example, when x goes from 1 to 2, because we went from 0 to 2, so larger values, for example, from 1 to 2 will make the higher powers not negligible, which means that the approximation will not, when x is equal to 1, for example, 1 over 6, 1 to the power 3, by itself is already not negligible enough. If it is to the power of 4, it is still going to be substantial. And that's why the approximation is not going to be accurate. And because the approximation is no longer accurate when we are dealing with bigger values for x, that is why the approximated for the integration version is also going to be not very, very good approximation. Okay, this is for part 4. And for part 5, we are going to make use of the strategy that I've highlighted in the theory outline on Achevas TV. It is on the second page of the Maclaurin's theory outline. So from the previous part, we have gotten this as the result, which is sine ln of 1 plus x. We know that this is equal to x minus half x squared plus 1 over 6x to the power of 3, and so on. So we have gotten this. And on the second page of the Maclaurin's outline on Achevas TV, I highlighted 5 methods to do this kind of question. One is definitely to make use of MF26, and the question has actually told us to use MF26. And the other one is to use trigonometric identity. I don't think I'm going to use it here. Differentiation, integration, and binomial expansion, or some algebraic manipulation. So if I have these 5 strategies to try for this, in order for me to get a cosine of ln 1 plus x, I'm going to differentiate this. Because I know the moment when I differentiate this, I'm going to get a cosine of ln 1 plus x. Chain rule, differentiating ln 1 plus x is 1 over 1 plus x. And differentiating the right hand side, this is 1 minus, differentiating this, it is going to be x. Differentiating this is going to be 1 over 2x squared. 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 1 over 2x squ Okay, we are executing a strategy that we have already prepared for. I don't need to wait till the A-level to try to react to something that is like this. It is on Achevas TV under Maclaurin's. On the second page of the Maclaurin's, I talk about how we can make use of differentiation to derive other Maclaurin's series like this. So we have a cosine of ln 1 plus x. This is going to be equal to 1 minus x plus 1 over 2x squared multiplied by 1 plus x. And we are supposed to expand all the way until the x square term. So this is going to be 1 plus x. Then this minus x square. This plus half x square. And so on. So my final answer is going to be 1 minus half x squared. Maxine, too few terms are used. I don't think so, Maxine. I don't think this will be correct. I don't think this will be acceptable. Yeah, I don't think this will be acceptable because, right, if you want to add more terms, as in like, I assume, Maxine, you're referring to this part 4 here. In order for you to get a better approximation, or the reason why this is not a good approximation is because you didn't write down enough terms. Which means that the suggestion is actually to write down more terms, which means that we will want to write down x to the power of 4, x to the power of 5, and so on. But then the thing is, the value of x that you're using is already pretty big. So writing down more terms will actually cause even more deviation to the entire series. So because the next few terms that you're going to be writing are still going to be substantial. Yeah, the next few terms that you're writing, right, will still be substantial. So I don't think writing down more terms will actually cause your integration to be better. Using smaller values of x will. Because writing more terms and making sure that the values of x are smaller and smaller will actually give you a better and better approximation. And I'm assuming, Maxine, you are the Maxine that I know. So in the tuition class, right, we were saying that when you're doing a Maclaurin's expansion, the values of x that you should be substituting that will give you a good approximation actually depends on whether you are expanding this in ascending or descending powers of x. Ascending or descending powers of x. So if you are looking at an ascending powers of x, when you're expanding in ascending powers of x, in order for you to make sure that the behind few terms which you are going to neglect are negligible enough to be neglected, you want to make sure that x is as small as possible. For example, 0.001, so that when it is x to the power of 4, 0.001 is going to be negligible. So you want x to be as small as possible. But if you are working on an infinite series where it is going to be in descending powers of x, for example, x to the power of minus 1, for example, in descending powers of x. So for example, x, then the next term is 1 over x, then the next term is 1 over x squared, then 1 over x to the power of 3. This is in descending powers of x because it is x to the power of minus 1, x to the power of 1, then x to the power of minus 1, x to the power of minus 2, x to the power of minus 3. When it is in descending powers of x, in fact, you want x to be as big as possible. The bigger the x, the better, the better the approximation, because the behind few terms will indeed become smaller and smaller and smaller. Right, Maxine? We talked about this during the class, I think 2 weeks back. So in this case, it is in ascending powers of x. So between the two possible reasons that I may want to give, I will probably go for the value of x to be bigger or smaller instead of writing down more terms. I think this will have a higher chance of us getting it correct during the exam. Okay. In fact, another student was asking me during tuition, and I was showing I was showing okay, I am glad, Maxine, that you can remember. I'm glad you remember this ascending descending powers of X thing that we discussed. Let me show you guys something that I showed my J1 students this week. This week we were doing Maclaurins. Let me see where I can find it. We were doing Maclaurins together, and I was showing them what that is going to happen, right, if you were to be drawing sine graph. For example, this. Let me show you something. If we were to be drawing sine graph, we will be expecting the wavy graph, correct? So, and this y2 is what I have gotten from the MF26. With one mistake, this should be to the power of 7. So this is my fault. Okay, so let me correct it. So this I should have type it as to the power of 7. And when you generate the graph, you will get something that is like this. So the blue colored graph is the sine graph, the original sine graph. And then the red colored graph is the Maclaurin's expanded polynomial version of the sine graph. And we can see from here, right? I've already typed in a lot of terms, but we can see from here that when I use smaller values of x, the approximation is incredible. It is almost exactly the same as the original sine graph. But when I use bigger and bigger values of x, they start to deviate. And that is why when we try to do integration, for example, if I were to integrate from 0 to 1, will it work? It will work. Oh, green color is not so easy to see. If I were to integrate from 0 to 1, will the approximation be good approximation? Yes, it will be, because I'm using small values of x. But if I were to integrate from 0 to, for example, 1, 2, 3, 4, 5, from 0 to 5, the approximation is going to be very inaccurate, because the red colored graph shows something that is like this, but the blue colored graph is totally something else. That is why using smaller values of x will give you better approximation. Even if you write down more terms, it is not going to change. Using smaller values of x will change it. Okay, let's look at one last question, and I thought this question is a very interesting question also. We'll be expecting this question appearing, this kind of question appearing in the A levels, this kind where we don't get numbers to substitute into our vectors. We are going to be just working on all the non-column vectors kind of vectors. Okay, in fact, when I was doing this, I found part 1 a bit ambiguous. So for part 1, A cross B is equal to 0. I want to find A dot B in terms of modulus of B. And I thought it is literally just going to be in terms of modulus of B, but we will need to introduce a constant ourselves. Okay, I didn't expect that, and I thought the question can be a little bit more clear about what they want, but no matter what, this is still good. This is still a very interesting question to try. So A cross B is equal to 0. This implies that vector A is parallel to vector B. Please take note, I'm using the word parallel. So A is parallel to B. This is different from us saying that A is in the same direction as B. So they are parallel, which means that they can be pointing in the same direction or they can be pointing in opposite directions. Which means that I know A is going to be equal to, for example, K times of B, where K here are just any real numbers. So it can be plus, it can be minus. And when I look at A dot B is going to be modulus of A, modulus of B, cosine theta. Modulus of A, I will definitely try to replace it by modulus of KB, which means that this is going to be modulus of KB this way, then modulus of B. As for theta, because A and B, theta is the angle that is between A and B, correct? So if A and B are parallel to each other, that means I'm expecting two possible values for theta, either 0 degrees or 180 degrees. Because they are parallel, that's why it can be either pointing in the same direction or pointing in the opposite direction. So I will go for cosine 0 degrees or modulus of KB mod B cosine of 180 degrees. So modulus of K, I'm going to just put it as modulus of K. Then we will have a mod B times mod B. This gives us a mod B square. And cosine 0 is 1. this version will be mod k, then mod b times mod b square. Cosine 180 degrees is -1. So we will be getting a plus or minus mod k. This is just a scalar number, then modulus of b square. So we can rewrite this as just simply h modulus of b square, where h can be either positive or negative real numbers. Okay, so we have this for part 1. And in part 2, a cross b is not equal to 0, which means that a and b, they are no longer going to be parallel to each other. Let me sketch a diagram so that we can visualize the second statement here. So now a and b are not parallel to each other and they are non-zero vectors. So they can be something that is like this. Let's say this is O, this is A. And then let's say here, let's say this is B. So according to the question, there's a point P, which is the foot of the perpendicular from A to OB. So we have this foot of the perpendicular, and this point here is P. And similarly for point Q, it is the foot of the perpendicular from B to A to OA. So from here, foot of the perpendicular. So this point here is point Q. And the question tells us that AP is equal to BQ. So AP is the same as this. We want to write down the length of AP and the length of BQ. We can make use of the magic triangle, and if you were to use the magic triangle, you will derive at this A cross B divided by modulus of B, this length. Where A, this is vector A, this is vector B. So to find this, it is A cross B divided by modulus of B. And as for BQ, if you were to use the magic triangle, you will derive at B cross A divided by modulus of A. So the question tells us that AP is equal to BQ. I'm going to go for that. AP is equal to BQ, which means that modulus of A cross B divided by modulus of B. This is modulus of B cross A divided by mod A. I'm going to keep this as it is. As for this, I'm going to rewrite it as minus A cross B divided by modulus of A. And modulus of A cross B is the same as modulus of minus A cross B is the same as modulus of A cross B. So I have A cross B divided by mod B is equal to modulus of A cross B divided by mod A. This tells me that modulus of A is equal to modulus of B, which is what the question should. Yeah, which is what the question wants me to show. So I further proven that this length is the same as this length. This is interesting, part 3. I thought it is, okay, I personally have not seen something that is like this, and I thought it is very innovative. It's a very, very innovative question. So it is given to us that the angle between A, vector A minus B. A minus B is this. Let me write down. So this is vector A minus B. With BA. So this is vector A minus B. And the angle that is between vector A, which is going in this direction, and vector A minus B, this angle in between, this angle here is phi. I want to show this. And I see a cosine theta. I see a cosine 2 phi. I'm wondering like why is it 2 phi, but it doesn't matter. At least there's a cosine and there's a dot product. So I think for the information that is given, we can try this A dot A minus B. Let's try this. And A dot A minus B is equal to modulus of A minus B. Cosine of the angle that is between them, cosine phi. I will definitely expand this dot so it will be a dot a, which will become modulus of a square, then minus a dot b. This is equal to modulus of a. This is the problem. Cosine phi I definitely want to keep, because hopefully I can do some double angle, double angle formula, trigonometric formulas, to try to re-express cosine phi to cosine 2 phi. But how about modulus of a minus b? So when I was looking at this, I was wondering, okay, for modulus of a minus b, should I work on a minus b itself? Or should I work on the entire modulus of a minus b? Because if I were to work on the entire modulus of a minus b, we don't really have a calculation for this modulus of a minus b. Neither do I have much calculation that can be done for a minus b itself. So I was thinking, why not? I will just see modulus of a minus b as literally this distance ab, this distance. So if I were to see it literally as this distance, it is just this distance ab, I realize I can calculate this distance by making use of the fact that this OA is the same as OB, which was what we proved here, right? OA is the same as OB. So if OA is the same as OB, we are looking at an isosceles triangle, which means that from the vertex, if I were to draw a line perpendicular to the base, it's going to cut the base into halves. And this length here is just going to be OA cosine phi. So this length here is going to be modulus of A cosine phi by making use of Tokaso. Modulus of A cosine phi, which means that AB is going to be 2 times of this. So if I can see this, then I'm going to rewrite this as 2 times of modulus of A cosine phi, then cosine phi. So I will have here, this is modulus of a square minus a dot b. This is modulus of a times modulus of a square. And I'm going to keep this as 2 cosine square phi. Because I know 2 cosine square phi is going to be equal to cosine 2 phi minus 1 using trigonometric identity. So this is modulus of a square. I will rewrite this as 2 cosine 2 phi. Sorry, not minus 1, but plus 1. Trigonometric identity changing from this to double angle. So I have a modulus of a square minus a dot b. This is modulus of a square. Then okay, sorry, there's no 2 here, my fault. So this, then cosine 2 phi, and plus modulus of a square. So modulus of a square can be cancelled. If I were to shift the -1 over to the other side, we will get what the question is wanting us to prove, minus modulus of a square, then cosine 2 phi. Okay, part 3. It's a very, very interesting question. In fact, B is also pretty interesting. BQ. Can BQ be... BQ is A cross B divided by mod A. BQ is A cross B divided by mod A, correct? BQ is A cross B divided by... Officially it should be, for BQ, right? For BQ, the more accurate version is actually this. So if you were to ask me, I will start off with this. If you were to go through the magic triangle, you will also be getting something that is a bit more similar to this. And we need to know that A cross B is different from B cross A. Actually, you can. Sorry. If you were to use the magic triangle, then yeah, you can actually potentially get A cross B also. So A cross B, B cross A. Yep. Yeah, I think you can directly write this as A cross B divided by modulus of A. You don't have to write this. Let me think. Yeah, you don't have to write this. Let me very quickly repeat this. Modulus of A minus B. It's actually very simple. Hello. Let me repeat again, okay? Because I see that modulus, we know that A minus B, the vector A minus B is this vector. So the modulus of this is basically this length. So I'm going to just try to find this length. Okay, we know that this angle here is phi. And from the previous part, we know that this distance, OA, is the same as OB. So we are working on an isosceles triangle where this is the base of the isosceles triangle. So if I were to draw a line down to cut it perpendicularly to the base, I'm going to be getting a perpendicular bisector, which means that this green colored line here, which cuts the base at 90 degrees, it is going to be cutting it into half. So if I were to focus on this triangle, this length here is modulus of A. So by using Torcaso, and this is phi, I know that this length here is modulus of A cosine theta, which means that this entire length here is going to be 2 times of modulus of A cosine phi, which gives us this 2 times of modulus of A cosine phi. So basically we have used geometry instead of using vectors. Because like what I was telling you, I was trying to calculate this using vectors. And I realized that A minus B itself, I cannot really do much calculation. Neither can I use that much of vectors to evaluate or calculate modulus of A minus B. So making use of the previous part, knowing the fact that for the triangle that I'm drawing here, it is an isosceles triangle, I deduce the value of modulus of A minus B by using geometry. Okay. And now let's take a look at the last part, B. B, we are looking at a pyramid where the volume of this pyramid is 35 units square. How do you get BQ, AP? For BQ and AP, right, it is the best is to use the magic triangle, but at the same time, we have standard enough scenarios to tackle BQ, AP. It is this scenario. If you were to look at the outline, or if you were to look at the theory outline on Achevas TV, or if you were to look at your school's notes, to find this distance, if this is A, if this is B, to find this distance is modulus of A cross B divided by modulus of B. So I basically use this to find AP. Then I customize it the same way for BQ. Okay, the distance, similarly for this distance, we know that it is A dot B divided by mod B. Okay. Preferably we are using magic triangle to derive the distances, but for efficiency's sake, I do think that it is also good to make use of part magic triangle, part memorization of the of the formulas like this and this. Especially if you were to look at this part 2, right? It is 2 marks, which means that they're going to be awarding 1 mark each. So going through the entire magic triangle process and writing them down is not exactly that efficient. So if you can just very quickly go through the magic triangle process in your head and then writing down as a formula, I think that is the most ideal. It is the best. Let's try the last part together. So we have a ORS as the triangular base, and OT is going to be the height. So let me draw the base. Maybe something that is like this. ORS. and t is the height. So let's say t, since it's the height, then means it must be 90 degrees to the base. So we have something that is like this. Okay, so this is our pyramid, and we are given the position vectors of r and s, which means that the coordinates of r is -4, 1, 3, and the coordinates of s is 5, 1, 0. I want to find the possible coordinates for t, and the volume of the pyramid is given to me as 35 units cubed. So I'm pretty sure we will be required to find the area of the base according to this formula, so that we can find the height, which is going to be part of this OT that we are supposed to find. So let's find the area of the base. To find the area of the base is going to be half of OR cross OS. So let's find OR cross OS. That is -413. This cross 510. And this cross this is going to get me a -3, 15, and -9. So the area of the base, area of triangle ORS, this is going to be half of modulus of OR cross OS. So this is half of modulus of -3, 15, -9. If you were to work this out, this is going to be half of square root of 3 square, 15 square, 9 square, adding them together, 315. Simplifying this is 3/2 square root of 35. Okay, so this is the area of ORS, which means that the volume, which is given to us as 35 units cubed, it will be 1/3 the base, 3/2 square root of 35, multiplied by the height, which is OT. This is equal to 35. So 3 and 3 can be cancelled. 2 I multiply over, it is 70 over square root of 35. This is OT. Not super necessary, but it's too tempting, so I'm going to rationalize this. It will be 2 square root of 35. So OT is 2 square root of 35. We only know the distance, and we know one more piece of information about OT, which is the fact that OT is going to be parallel, not the same direction, right? That's different. We know OT is going to be parallel to OR cross OS, since OT is perpendicular to both OR and OS at the same time. So OT is going to be parallel to -3, 15, -9. And of course, I can use a simpler vector. We can use a 1, -5, 3. So we know that T, let me use red color. We know that OT, the vector OT is going to be parallel to 1, -5, 3. And it is going to have a magnitude of 2 square root of 35. So now we can quote OT, the vector OT. It will have this magnitude. And as for the direction wise, we are going to use the unit vector of 1, -5, 3. Because the unit vector has a magnitude of just 1. So multiply by whatever, you will just scale it to the magnitude of 2 square root of 35. So, and because it is in the same direction as this, but not necessarily in the same, it is parallel to this 1, -5, 3, but it is not necessarily that it is going to be in the same direction as this. So I'm going to put a plus minus of 1, -5, 3 divided by the modulus of 1, -5, 3. No? Oh, as in like the pyramid, the pyramid has 2 right-angled triangles. Yes, as in like here and here, right? These are the two here. This one right-angled triangle and another right-angled triangle. It happened to it will be one pyramid that has two right-angled triangle. Because the question says that the pyramid is ORST, and OT is the height. If they were to say that there's a point that is in the center to T is the height, then we don't have two right-angled triangle. But because the question says OT is the height, so OT must be perpendicular to the base. So this is going to be plus or minus 2 square root of 35, and this is 1 minus 5 3 divided by modulus of this 1 square, 25 square, 35 and 9 square. This is going to be square root of 35. So I've gotten my answer. This is going to be plus or minus 2, 1 minus 5 3, and we are supposed to write down the coordinates of t. T will be, if it is minus 2, so T will be minus 2, 10, minus 6, or another possible coordinate of T will be when this is positive 2, then it will be 2 minus 10, 6. Okay, this is the last question that we're going to be doing. Superb. 9:30. For our last stream, we managed to finish at 9:33, which is probably one of the most accurate, and it's pretty good. I should have probably done this. I'm not sure whether I'm going to be doing live stream next year, but I think I should probably do less question so that there will be more time for discussion. Or else for the last few live stream, right? I don't mind discussing. It's just that I also plan more questions to be done